So we have 4 classes, and today I will complete the hydrogen atom problem. I mean, if all the calculus way of solving. Why so many people are joining online? So what is happening today? Why so few people? Do you know? Is there anything? If- Oh, today there is a quiz. Oh, okay, okay. I see. Okay. Okay, so what we will do is that we will discuss the calculus way of the hydrogen atom problem, and then in the remaining 3 class, what I will do is a very deep topic actually. It's the formalism of symmetry and angular momentum, and unfortunately, I have only 3 class to do that. So I'll do whatever I can, and there is a possibility that I won't be able to finish it properly. So I might do a extra class on Saturday where those who are interested can join. It won't be in exam. In case I face a situation where I cannot finish the angular momentum algebra, it's completely a class for someone who is curious and want to learn, uh, not compulsory, not for exam. If you want it, okay, and yeah. Next Saturday. After all the classes are over, some Saturday morning, if you want, or because this chapter is actually very profound, but and it's but every time and this time especially it happened that we have only 3 lectures for it. So I will try to do as much as I can. If I manage to finish, then it is fine. Okay, so and I don't want to repeat those stuff in quantum mechanics too. So that's why I want to just wrap it wherever it is. Those who are not taking quantum 2, they don't need to care. But if you're taking it, it's useful to know. Okay, so we are back to spherical symmetric problems. Let's start recording. Yes. Okay. And as I stated earlier, the Hamiltonian is of this form. This is the problem we set out to solve. Actually, the full problem is this. And the problem we set out to solve is this. Where psi is RT. And we also stated that this operator is nothing but minus h car square by 2m. This part is nothing but some complex calculus and algebra. There is nothing new conceptually. We have learned all this. So it is only a matter of sitting down and internalizing it, and it can be completely self-study, unlike the first part. So if you are not understanding anything, just sit for some time. You will understand. There is nothing more complicated. Okay, so this part, we said that. Okay, what was the form of L square? Ah. So grad square L square is of the form 1 by r square s theta del theta s theta del theta plus 1 by r square s square theta del phi. Okay, and we also showed that these three forms a CSCO. Although there are more conserved quantity, but we choose these 3 mutually commuting quantities to get the CSCO, and therefore I want to find the common eigenstate of Lz and L square. So I set out to do that. Okay, and we found that by solving this associated Legendre equation, So the L square operator is of this form. So we said that they have common eigenstate. So Lz, so we call them, they can be labeled with a common eigenstate. So YLM. Did somebody try to answer this question? Why it is L into L plus 1? Why, at least do you know, understand that it must be at least L square, but why L into L plus 1? So this is to accommodate the possibility of spin half. So if you plot L into L plus 1, you will see the minima is at half. So although so far I have not talked about spin, I'll talk about spin in the next class. This is just angular momentum. But since spin is like an angular momentum, you want to have a possibility that what happens when it is half. Think about this more. That why did I choose without any loss of generality? I can choose that, but why did I choose that? Okay? Think about it more. Okay, so I want to solve this common eigenstate. I want to find the YLM, which is common eigenstate of this L square and Lz. And this is what we discussed to be the spherical harmonics. So we first of all we found that the phi part must be e to the power I phi just by the same token. It has to satisfy uh, this compact. It's a compact parameter, so because it identified itself at origin. So the phi part was that. So this was the solution we found. YLM. This is a purely a function of theta and phi and nothing else. So it must be only theta and phi. So YLM we found to be 2L plus 1 by 4 pi L minus M factorial by L plus M factorial. I showed you how to solve at least I showed the outline of how to solve it when M equal to 0. When M is non-zero, it is a bit complicated, and it's not worth showing it in the class. But if you are curious, you can just search it in any of the math method. Usually, quantum mechanics books also don't show it; they just refer it to math methods books. So. So the theta and phi can be separated because it's a separation of variable form. Oh, I missed a square root. This was the form. The M must be an integer, and we found that M mod must be greater than L. So that means if L is 0, 1, 2, 3, these are the allowed values of L. So M must be whatever the value for each value of L. So L is 0. If it is 1, it is 1, 0, minus 1. If it's 2, 2, 1, 0, minus 1, minus 2, because this has to be satisfied. So M will go from minus L to plus L. Okay. So this is what we have found about the structure of this solution. For historical reason, this L is called azimuthyl UN. M is, what was M called? Some magnetic. There is no spin yet. I will talk about spin later, but there is just these things. All these things people have discovered there are some quantum number that can characterize the spectroscopic things in early 1900, but it was around I think 1930 or so. Then people formulated quantum mechanics and derived this from the formalism, which matched exactly with the experiments. So if you look at a little bit in the history, they predict the spectral lines, etc., which exactly matches with experiment. Very good accuracy. And these numbers were given, these names were given before the formalism. So that's why the names are a bit strange. And quantum number generally refers to an integer level of a quantum state. So you will come across this quantum number in many different contexts. And in chemistry, they came up with, and even in spectroscopy, they came up with some other way of remembering them, S, P, D, F orbitals and all that. S means L equal to 0, P is L equal to 1, and so on. Okay? Just labeling, it's just relabeling the same thing. Okay, so this was what we already talked about. So now I will talk about the radial part, which I talked a little bit last time. So the full solution must have a radial part and this, whatever is there. This is not the full solution, this is only the solution in this subspace. Now I want the full solution, which is common eigenstate of all these three operators. So this is what I'll try to do. So this is something, the calculations will get complicated, but don't lose sight of what is actually we are doing. At least in class, in real time in class, you should understand the strategy and the overall picture. You may not everyone can follow a lot of algebra in class. I couldn't when I was a student. But if you can, that's great. But even if you cannot, don't lose the sight of the overall picture. Okay, so now I plug this thing into this form of the Hamiltonian and this equation. So if I do that, then what I get is, I also wrote down this last time. I need not write it again. I get this form. This is just a different way of writing things. Del R squared. There is one small algebraic step, one small calculus and algebra step involved, which allows you to write it this form. I described it last time. I'm not repeating it again. There are certain advantages. This algebraic step that I showed last time allows you to write it in this form, and therefore you can finally write the full equation by introducing a new function called u r times r and rewrite this whole thing as in a very neat form. Now there is a mathematical reason to do that, because it's just a neat, compact, convenient form and resemblance in 1D problem, but there is a physical reason also. So let me explain the physical reason after I write the mathematical form. Okay, this is the radial equation written in terms of this u, and where I just multiplied the actual radial part with a r, which I can do without loss of originality. But the reason why I do it, because I know this r part will be some ur by r. Anybody knows why should I guess such a form? Did you study spherical waves, cylindrical waves, all these things in your wave oscillation course? That's definitely true, but there is also a physical intuition behind it. That of course I show you. It's just a prescription. That do this substitute, you get that. But when you are doing this problem for the first time, somebody is doing. Why do they do such a thing? Why will they think in that line? Okay, that is the question. Okay? Then you have some hope of when you do a solve. If somebody shows you the solutions and everything in a book, you will know, okay, fine, it can be done. But think of a creator point of view. Why will they think such a thing? So did any of you remember spherical wave, cylindrical wave? So you studied plane waves, right? So plane wave is something that propagates like this, right? Spherical wave is something that propagates like these concentric spheres. And cylindrical wave is something that propagates like a concentric cylinders. This comes from a point source, this comes from an infinite source, and this comes from a line source. Studied all this. Do you know the mathematical form of them? One person nods, other person blank. What? This is 1 by r, right? This is e to the power I k x minus omega t. This is e to the power I k r minus omega t divided by r. And this is by r square, right? You know that. So if I have this is a spherical form of solution, and if I want the solution to resemble a spherical wave, in the absence of any potential, it will be just a plane wave. Okay? The spherical plane wave have this 1 by r. So this is the reason why any book you open, you will see they will just write this. But why? Why do somebody thought of writing into this, doing this strange substitution? Okay, this is the reason. Now, why 1 by r comes there? Do you know a physical reason? Why 1 by r? You know it is there, but why it is there? What is it trying to do? Yeah, of course, I know what it is, but why is it there? So think about it. It is because of energy conservation. You want the plane to contain the same energy, same phase. So they must satisfy some structure in order to do that. So this is the same reason why I told you why gravity and Coulomb have same form, because they have the same goal. If you start with a point source, point charge, point mass, if you go up r distance, you cover a surface, the number of flux line should be same. This is why gravity is 1 by r square, and Coulomb is also 1 by r square. It's not a random coincidence. It's because of that conservation. And if you go to 2D, it will be a different form. You'll get logarithmic gravity. Okay, so you should ask such questions always and try to figure out. They are not always discussed explicitly. Okay, so now I have reduced my whole problem into this 1D problem. Since my potential doesn't have a theta phi dependence, this is the only part which varies problem to problem. If I give you different problems of within the spherically symmetric class, all problems that has spherical symmetry, the theta phi part is not going to change. Only this is going to change. So no matter how complicated it is, you have to solve one equation. One equation in half line. Half line means r goes from 0 to infinity. That is the difference. It's a 1D equation, but in half line. It has a potential which always have this part plus the whatever problem you are doing. Okay, that's it. So there is again, you can say a lot of things about this problem without actually solving anything. Like just sketch the solution. For example, let's say your VR is of this form. So let me call this whole thing as V effective. Is your effective potential. There is an additional term because of centrifugal force. This is the centrifugal part. So V effective, let's say it is A by R square. A by R square is this term minus B by R. So this is an attractive potential. So attractive potential, if you sketch it, you must have done this kind of things. It will look like this. Did you do central force now in classical mechanics? Oh, so then you know when you will have a bound state, a bound orbit, periodic orbit, when you had ellipsoid, when the particle will escape to infinity. Just same thing. This is like why planets rotate, why comets go away, all the same strategy. So here instead, of course, things will be in terms of probability, and there is, even if it is supposed to be bound, there is a finite probability to leak, and all those things will be there. So if this is attractive, so I can also do the repulsive problem, which is A by R square plus B by R, and then you will see it will look something like this. So at this energy you can get a bound state, but at this energy you cannot get a bound state. All these things are applicable, whatever you learned before. So I will not go too much into this intuitive solution, but rather I will do the formal solution. So my psi E L M is r theta phi is u E L r phi r y L M theta phi. So this solution, this u, I am putting it. It is of course a solution of energy, but it's also a function of L, because as the L is higher, this potential is going to change. So that's why I'm putting a L level also in that. So I have to solve an equation of this form with some normalization. The y part normalization we already did. So this part also you have to normalize as that the probability is 1. And it will boil down to a only a one variable problem, because you know, if I have to do this d3x psi square equal to 1, then this is nothing but r square dr d omega. This is the solid angle u e l mod square y r square y lm star y lm. So this spherical harmonics, these y lms are orthogonal function. You can work out this condition from the orthogonality, and this will boil down to solving this 0 to infinity. This will get, you can get rid of them by orthogonality. So dr u e l mod square equal to 1. So this is all you have to solve in order to find the normalization, that n. Okay. So this is the premises of the problem. There are two more things, that is boundary condition. That since it's a second order differential equation, you need boundary conditions. So one boundary condition is obvious. That is basically limit r going to 0, ur is 0. This comes because of the fact, because if it is not going to 0, at least at a rate faster than at the rate at which r is going to blow up, then your solution is going to blow up at origin. That you don't want, right? Because r is going to blow up at origin. Right? So you must normalize that. That is what we also did earlier, that exponentially growing solution, so that must go to 0. Now there is also intuitive way of seeing this, at least that is going to happen in this problem, because this potential is going to infinity. Okay? Why? Because 1 by r square is always there. There is 1 by r square. It's very hard to beat that term unless you are doing something, unless you have a potential which is even stronger than that. But that is also not going to beat it. It's always going to go towards infinity. So it's very hard for the particle to be, it is going to be more and more hard for a particle to be found at closer to 0. So that's why that also justifies this boundary condition. So there is actually other ways of seeing it, where you can put this form, make it a finite thing, and if you put it in this equation, just like the Laplace equation for a point source, you will find this delta function, which is hard to justify in order for energy conservation, but this is at least one intuitive way to see that. So now other limits. So now let's look at the other limit. The other limit is problem dependent, that is not generic. So let me write the other limit. So I hope everybody is following. It's complex, but it's very simple. It just needs to do it carefully once. And it's also advisable that you sit down through it. It is unlikely I'm going to ask you this kind of things in exam, because they are too complicated for exams. But it should be in your head, because they are used everywhere. Any course you take, like spectroscopy or anything that depends on this. So in fact, these are the most useful part. Like sometimes the whole chemistry courses are built on this. That this is the most practical part. It connects to experiment. All this abstract. This is another thing you must appreciate at this point. All this abstract philosophical thing we discussed, they boils down to a measurable lab. This is the beautiful thing about physics. It's rarely you will find in one subject things that comes in lab and application, and also things are very philosophical and like raises the question what you can know or cannot know, that kind of philosophical. Okay, so let's continue on the other limit. So we discussed the r going to 0, now the r going to infinity. So there are two, r goes from 0 to infinity. So one boundary is this, other boundary is at infinity. So that this part is of always not same. So r going to infinity. Let us say I am discussing a problem where the Vr goes to 0 at any distance. So this can happen in many problems. For example, even Coulomb potential, it falls to 0. And or any other, like let's say a bound potential, but it need not be always. For example, this harmonic oscillator, if I have a 3D spherically symmetric harmonic oscillator, that is not true. So when this is true, actually I will show you in a moment, a more useful condition is this. This thing is going to 0. This thing is going to 0, which means Vr is falling at r going to infinity, but falling faster than r. That is not true for Coulomb potential, because Coulomb is 1 by r. So 1 by r is doesn't go to 0. We have to think differently, which I'll do today. But at least when this happens, so let's see then what can you say about the solution for the class of problem when this is true. For certain problems. It's not general because it is not true for many cases, so we'll discuss that also. So then the asymptotic solution will be this. Yeah, because this term will fall off, and the B and this both will fall off because Vr is going to 0, and this will imply we have to solve this equation that U del R2 EL, just like the way we did before. We call this some kappa square something. So this is the equation we must be solving. Okay, and again as usual, you will have these two kind of solution: E less than 0, E greater than 0. One is oscillatory, one is bound. Okay? One is exponential. So UEL will be less than 0, will be bound state. This will be the oscillatory state. So if I sketch this solution without solving, I know that this is going to look like this. So I claim that this will going to 0 at origin. So this will be the form, and at infinity it must also. In this case, this is the infinity solution. One case it decays, and in the other case it is oscillatory. Right? So somehow you have to stitch the solution in the middle. These are the asymptotic solution. So they will have a nodal line on etc. That depends on the details of the problem, at which level the node theorem etc. will come. But this is basically the structure of the problem. This is the bound state. So this is U. I am plotting U, okay, not the full wave function. The full wave function is U by R. So this is the bound state, and this is scattering state. Okay. So now let's solve some problems. Look at the solution of the problem, because the solving itself might be a little complicated. Yes. Sorry. Yes. No, we didn't assume. It's just a redefinition. R is a function of R. Right. I can keep whatever R function is, I can write it in this form. The rest of it. So if R is, let's say, if R is R to the power L, so then it is R to the power L minus 1. I can rewrite it in this form. Right. So that is all. So the U, I call it just this, and I call this, I relabel this as R. Or something else, anything I can do that, right? It's just splitting this into two parts. So U is just U, R is just U by R. That's all, nothing else. What? Yeah, because I know that R is going to 0, right? R is going to 0 means this is going to blow up. So I am setting the U to be 0. So the whole equation now boils down to a U equation. So since it's a differential equation on U, I want to have a boundary condition in terms of U. So if that happens, then R also goes to 0, right? If U is going to 0 like that, then R is also going to 0 at the origin. And I am justifying why that might be the case because of this term. Physically speaking, this is because of this term. Because this term is going to make it infinitely difficult to reach actually at the origin, right? So is that your question, right? That U is not a physical object, R is the physical object. So why am setting the boundary condition in terms of U? And if I am setting in terms of U, what does it imply for R, right? So the answer is this: since my differential equation in terms of U, I am saying it in terms of U, but it implies for R that R also goes to 0 at the origin. And why it must be is because of the centrifugal term. The centrifugal term makes it very difficult for the particle to collapse at the origin. Okay? Yeah, so here I'm plotting UR because everything is in terms of UR. But when you plot the actual wave function, you plot U by R. Yes, I'll show you such plots also. Make sense? Okay. Okay, so now let's look at some solutions. Some simple problem we'll solve, then we'll do the hydrogen atom. Okay. Everybody in the same page? If you have taken the pain to come today while there is a quiz, you better make it this 1 hour useful. See, the class needs to be like, you should make the most of the class, because otherwise this is it's very hard to self study these things. It's not hard, but it takes a lot of time. So if you understand things in class, the self study part becomes very easy. Okay, so now let's talk about some types of problems. This is a spectrum of all the problems that are generally falls in this category and usually taught in a master's level course. So one is of course the free particle. Free particle means the V is 0 or constant. Then all the problems we did so far, same thing. Spherical well, which means it's 0 in a sphere and infinite outside. And all the problems we did so far, isotropic SHO. And finally, this is a problem which we didn't do earlier, Coulomb potential. There is actually another interesting problem, that is inverse square potential. I will not do it, but those who are interested, they can do it. I will refer to literature. This problem is very unusual. The potential is 1 by r squared. You can show this as something called conformal symmetry, and that is you have to apply various. It becomes very strange, and you require things like renormalization and regularization to solve that problem, which are very useful concepts. And I wish I had a day just to teach that, and that would be very nice. Usually it is not taught, but I encourage you to look into this. But these four are typical syllabus anywhere. Okay? And delta function, which is, I may not do it, but we did it earlier, it will be similar. Okay, so let's start with the free particle. Again, all you have to do, you solve these problems already, except the Coulomb, but in a line. Okay? Here you have to solve it in half line. That's the difference. Okay? Okay, I should have used mu here because m is used for a this YLM. So mass, I will call it mu. Mu is basically the actual notation for reduced mass in a two-particle frame, and but we will use it generally as mu because m is used elsewhere. So don't get intimidated by seeing, oh, this is so many things. But this is, if you think like that, then higher education will feel like a load. But it is not a load because it's same problem, just slightly differently. That is another thing. When you start getting it, you see it's very few things actually we can do. We use this everywhere. Okay? So this is a classic example of that. There is a saying, the only problem we can solve is hydrogen atom and harmonic oscillator. The only integral in physics we can do is Gaussian integral. Everything is based on those few things that we can do. And once you understand that, then you'll realize that is actually the nice thing about physics. There are very few things actually you have to remember. Everything is connected to those few things.
Sir, it is 2 mu r square.
Yeah, say that again.
Is it the 2 mu r square instead of 2 mr square that you have written?
What is he saying? Can somebody hear clearly?
So I will write it in the chat.
Can you write it? Because somehow your voice, maybe it's a mic setting problem, is echoing. Can you type it, your comment? Is it some problem with connection or board visibility, or it's a question? Okay, anyway, let him type it. Okay. Oh, yeah, yeah, yeah. You first saying that, yeah, very good. Because this is mass. Mu is mass. Okay. Okay, good. So this is again as usual. I'll massage the equation a little, and then it becomes d2 dr2 plus k square. So just to make it a little sleek in form, compressing the notation, and we can do another variable transformation called kr just by absorbing this k inside, and then it becomes d2 d rho 2 plus l into l plus 1 is same as harmonic oscillator, the way we absorb the various hanging constants and change the dimensionality. Okay. So this is the form, a very neat form, and it's a familiar form. If you have already solved it, you might recognize it immediately. It's somewhere in math methods or differential equation. This is actually a Bessel function. It's a Bessel equation, and the solution is a Bessel function. So the solution will be of this form. JL rho, so rho is Kr, and if I take the m equal to 0, this is the spherical, just the pure L equal to 0 forming. This is just the spherical Bessel function. Now you can write it in a asymptotic, like J. Of course, J is something which you don't know unless I write it properly. You won't have any intuition what is it. So let me write it for m equal to 0 case. What U? This is the solution, the UEL, so solution of this equation when L is 0. Sorry, L is there, M is 0, the no M part. Actually, this solution will not have any M part, M will come from the spherical harmonics. Okay? This is just the solution of this. Actually, I should have written this first and then this. It would have made more sense. This has a rho, so psi is U by R, so that cuts that rho. So that's why it comes in this form. Okay, so R going to infinity. So I'll just write down the solution and then tell you a little bit how it helps in many cases. So UEL, this R going to infinity limit, this Bessel form looks like, this whole U looks like sine AR minus L pi by 2. Okay. So the actual R means it looks like this by R, sine by R. Now, interesting thing is, it turns out you can show this that if there is a finite well somewhere in the middle, somewhere in the solution space, and if you want to calculate the R going to infinity limit, then you can show it looks like this. This is just free particle, right? But this is, the space is free everywhere except at some finite region. There is a spherical boundary, spherical barrier. Then this solution gets a phase shift, which is a function of the depth and all that. So actually we will do this kind of problem in detail in quantum mechanics 2, in scattering chapter. But I just wanted to demonstrate this result to show you that even if you are catching a particle or seeing a particle at a distance, see, nothing is like it's, if you are doing an experiment, let's say, where there is no potential nowhere, versus you are doing an experiment where you have a potential somewhere and you are seeing the particle far away from it. So it's like a free particle far away from it. But it carries the information in the form of a phase that it have seen a potential somewhere. Okay? This is a very interesting result, and this is actually the idea that allows you to do these experiments like this particle collider and all that, where you catch the particle far from the event where things clashed with each other and things happen, and it carries the information that what happened there. This is also the reason why you do this, think of this cosmic ray experiment. They carries information about somewhere far apart in universe, some event that happened, and all that. Okay? So this has a very far-reaching implication. In case you are feeling, sometimes we feel, oh, differential equation, dry exercise, but they have very far-reaching consequences. Okay, so let's talk about the next problem, which is particle in a infinite well. This is the first problem. So infinite well means what? That VR there is some spherical region in space where the potential is 0, outside it is infinity. So then inside the well, we have done the particle in a box. It's basically that. There you had the sine wave function with n square dependence, energy depending on n quantum number and n square. So this will be this is also something you will appreciate. These statements I kept. This is the Anderson statement. The physicist's job is not just to solve a problem, but to set up that any fool can solve it. The formalism is so powerful. It's anybody can solve it. What is there? There is a differential equation. But there is some catch also. You will see most problems that we actually care about are not so simple to solve. So that is a whole discussion. In quantum mechanics 2, we will deal with that. Some of that. And most problems, and then there are problems which where you don't have any traction actually. So sometimes you are feeling like, okay, it's so complicated, but that's a blessing. So when you see the research problem, then you will see that you don't even know how to start, how to define. So you at least know there is a way to proceed here. Okay? There is a traction at least. There is no traction in most modern problems. So then people try to figure out how to do it. So if you're feeling like, oh, a lot of calculation and all, but then after a few years you will feel like, oh, let there be something that is calculable. And then it will become incalculable problem. Okay, so this is the form, and it must satisfy that UA is 0. Okay. Along with the fact that U0 is 0, U0 tends to 0, UA is also 0. Notice that U0, 0 going to 0 will always be true because of this infinite wall. That wall is going to blow up anyways at the origin. Right? So that will be anyways true, but in addition, because of this will be true here. Okay? So then if you turn the crank, you will see that for L equal to 0, the solution will be in 0, 0. It is expected solution. It is just like particle in a box, n pi Ra, but with a 1 by R because spherical. And En0 will be pi square n square h cut square by twice m square, twice m a square. This is the L equal to 0 solution. The L not equal to 0 solution will of course depend on L because this part is there, and that will be again some spherical Bessel function. So let me just write it down here. So these things are spherical Bessel function. These are called spherical Newman function, some name, but it is basically one can get it again by doing this series solution or this form. And if you plot them, you can see that for each L, they are like different problems, right? Because if once I freeze the L, then I freeze the problem. Right? So you can plot the L equal to 0 solution, for example, they will become these n square levels. L equal to 1 solution will be something like this, and so on. So you can plot them ENL like that. This is a useful way to solve, useful way to represent, because often you want to know the spectroscopy outcomes. For example, you know if these transitions here to here or here to here. So that's why these energy level diagrams are sometimes useful. Okay, there is one more problem which I will not talk about, but rather I will move to the Coulomb problem. That is this oscillator. Okay, let me talk a little bit about it. Okay, all the problems we have discussed so far had this structure. The particle in a box. Now let's do something where this is not true. No, it is infinity. not going to 0, and example is oscillator. Or coulomb. Okay, so now we will discuss this solution. But let me give you a little intuitive idea that why do we need to think in terms of RVR and not VR alone. So the idea you can think is as follows. Okay, so let's say I have this equation in this form. Okay? And I think of a solution that it is going to be R going to infinity limit. So in R going to infinity limit, this term is not important, and I expect only this term to hold. And for a slowly varying function, I expect that UE is of the form sum effort times e to the power I k r. This is almost free particle, but what did I assume here? I assume that VR is slowly varying. That's why I can think this as almost like a constant, effectively a constant. That's why I can write it. So then this becomes two I k f prime minus 2 mu VR by h cut square if. So this is my form of the equation. And if r is also slowly varying, because VR is also slowly varying, so I can ignore the f double prime. The f is also weak. So the solution will be of this form. This is an asymptotic solution. Depending on if it is bound state or I will have a plus minus. So minus plus I k mu by r square dr if no dr because I have taken the f here and sent the r. So if I solve it, this becomes, this is a first order equation. Its solution is f r naught e to the power minus plus I mu by k h cut square r0 to r dr prime dr prime. Okay, this is the form of the solution, and as we can see that here if my r vr goes to 0 as r going to infinity, if it is slowly varying function, you can effectively call this integral, it will give you r vr. We can take r going to infinity limit in this integral, and then the fr will become constant as r going to infinity. Okay. So this is a sketchy way to see that if you have this RVR is going to 0, then this thing will become a constant effectively. This whole thing will become a constant. This definite integral. But if that is not the case, so let's say RVR is going to some constant that is not equal to 0, then you cannot write it anymore as a FR naught form. You will get a, so let's say the VR is like that, minus some constant divided by R. Then it will not happen, like Coulomb form. Then you can show your FR will be So that means the presence of the potential will be always there, and then you need to the information about the potential is always there because of this logarithmic form, and your full solution will be the plane wave will be of this form. So you will have a plane wave, but masked by this factor. It is actually a power law because log e to the power log is basically a polynomial, or whatever is there inside the log, that is r times that. And this intuitive solution, this intuitive form, we are going to use it to guess our trial solution when we will solve this problem. So I think I am up in time. So I will just initiate the hydrogen atom in next 1 minute, and then we'll take it up next time. I thought I'll finish the hydrogen atom today, but okay. So we'll solve. Next thing we'll do is this hydrogen atom, which is one nucleus and one electron. And let's say the nucleus is of mass m, this is of mass small m, and the potential is minus z square by r. This is the Coulomb potential, right? So it's the charge of Ze at the origin, and this is the charge of E, where Z is the atomic number, the nuclear number. So this is you know this kind of the basic outline of the Coulomb problem, right? You have solved the classical form, Bohr's equation, everything. Do you know this thing that did you learn it in electrodynamics or somewhere, that in a classical sense such a thing cannot be stable? Sorry, will radiate. Yeah, so classically this will always fall. Right. There is actually very exciting history about this. That stability of atom was a big problem at that time. So then that's why people realize the classical mechanics is not enough. Anyway, let's not take up your time because usually Yornima complains. So because I hold you too much. So just to say this, that this m, this is m and this is m. This ratio is almost 1 by 2000. So although when there are two equivalent particles have like are interacting via central force, you know by classical mechanics, they are basically orbiting each other. But the center of that orbit is located somewhere here, towards the heavier mass. Just like Earth and Moon or Earth and Sun, they are orbiting each other, but the orbiting center is almost close and close to here. So with this kind of ratio, you can effectively think this is fixed. This is not orbiting, and only the other one is orbiting, and that is how we will set up the problem, and we'll discuss the solution next time. Now there is no time, and that's all for today. Okay? If you didn't follow all the steps of this part because I rushed it a bit, just know that this much, that this is the condition. This condition is enough. This condition is enough, and we will see this intuitive solution, although we don't need it, but this intuitive solution to guess the form of the solution in the hydrogen atom problem. Griffith. Yeah. Any book you have it. Shankar is also has it. Griffith also. But Griffith is good enough for it. Griffith is usually easy to follow. In quantum?
I mean, scattering experiments in quantum mechanics.
Hmm.
So, how do we derive from this concept? How do we get the Hamiltonian, and how do we come to the example Rutherford scattering? How do we so quantum?
So are you saying if given the Hamiltonian, how can we say about this? That we'll learn in quantum too. Here I'm just giving an example that why these problems are important. You will learn, but here you learned a little bit already. I told you that if I have a barrier, if I have an incident wave, how much will be reflected, how much will be transmitted, right? This is the same problem. This one you learn, but this is the same problem in 3D. In 3D, you have a region which instead of a barrier, you have a 1 by r potential. Now you are throwing a particle, which is like a wave, which is a spherical wave actually, and then it encountering this, then it will scatter. So how it will scatter, that is what we'll learn in quantum 2. Same problem, just 3D.